real world. This time I'd like to introduce to you the simulation app PROTON.EXE. This has a very long story. I had started to analyze the metabolism of sulfate-reducing bacteria, and I found out that there are various protein-related processes going on, like uptake of sulfate in symport with protons, like vectorial proton translocation during electron transport, and finally that there were pH changes going on when sulfate was reduced to H2S, that was consuming protons. And I tried to understand this and wrote a first version of my simulation software, and that was called at that time Protonen-Translokations-Simulationsprogramm, still in German. Not so many parameters, but it already worked quite well. I can show you some very old experiments. So this was something I did in 1985, and I simulated it in 1986. And I added hydrogen to a cell suspension of desulfovibrio. And you see here the proton curve in red. And you see there's something going on, strange curve. And the simulation is here. And then I added 10 instead of 100 H2. And this is shown here. The simulation is there. And finally I added 50 and I got a signal like that, and the simulation is here. And together with that I simulated the H2S formation, which was measured at that time. Everything on paper, of course. And the sulfide formation was simulated as well. And actually the parameters here in the simulation only differed by the amount of electron donor added. So you can see 110 and 50. And by the drift, because I had some drift effects here in my experiments. Okay, this was quite helpful and interesting, but it was never published. And before I retired in 2018, I thought about maybe we should make a little publication about this. And I wrote a new version of the simulation software and called it PROTON.EXE. And more important, I found a master student, excellent master student, Jan-Ole Reese, my co-author. And we started to simulate all data, and he did as well new experiments, grew the cells in a chemostat, and analyzed the pH effects in new experiments that were simulated as well. And the new simulation software included the membrane potential, the delta pH, and the ATP as well, ATP formation. And that means you could learn quite a lot about bioenergetics when you apply this little app. It's freeware, okay, it's primarily simulating the metabolic processes to explain the pH effects, but you really can learn about the membrane potential, delta pH and ATP, and just go to the microbial world /proton.htm to see tutorial videos and download the app to try what you can do with it. Okay, we also wrote a publication that is now in the frontiers of microbiology, and this can also be found. It's open access on the same address in the internet, microbial world proton /. Okay, and I would like to shortly explain what you have to put into the simulation and what you get out. And the real-time application is shown in 3 more tutorials showing the application on different physiological situations. But in general, you have 3 panels here. The green one is with the bio numbers, the blue one with the technical settings, and the red one with additions and reactions. And biological parameters could be the cell optical density. How many cells do you have when you have 1 ml of OD1? And how big is the cell? What is the cell surface? If you don't know these numbers, it doesn't matter. Those given in the start situation are reasonable, and you can play with it. And it's even explained in the manual how you calculate the cell surface, for example. So I'm not explaining all the details here. Quite important is the buffering capacity of the cytoplasm. This is very big. What is the intercellular pH? What is the membrane potential? Yeah, and how many protons does the ATP synthase require per ATP? And how fast is it? And what is the proton translocation system, the electron transport chain, doing? How many protons are there translocated when one electron is going along the respiratory chain? Okay, you can play with these numbers and see what would be the outcome for the pH curves. And the technical settings include the assay volume, the buffering capacity of the outer bulk medium, the electrode response time, so it will not see within a millisecond all the protons that disappeared. There's some reaction time that you have to consider. And how long will you look at the experiment? So I should say the program calculates the results for every second, but you could also make it show it only for every 6th second or 5th second, whatever you want, and stop after some time. And all these things will be demonstrated in the further tutorials. And last not least, the additions and reactions that we have. You can add an electron acceptor, could be sulfate, could also be nitrate, could be oxygen, doesn't matter, but of course I thought about sulfate. And you could add an electron donor, and the most simple one is hydrogen that we quite often use. And then you describe what happens to the electron acceptor. So sulfate would, for example, take 8 electrons to get reduced. Then we have the sulfate uptake process. Does this have a proton effect? Yes, if there is proton symport, you will see disappearance of 2 protons. You can describe it here. And all the processes are also described by means of the Michaelis-Menten kinetics, and that means they get a Vmax, that is the maximum rate that can happen if there is sufficient substrate available. And when this is running short, then you will get a slowdown, and this is described by the Km value. And you can assume that the Km value is big or small, and you will see what this makes for the outcome of your experiment. And you can learn quite a lot about this Michaelis-Menten kinetics as well. So we have the uptake and we have the reduction, separate processes. You have again Vmax and Km values, and you have a pH effect when your electron acceptor is reduced, and what happens if it is released. All these steps can be described in this panel here. And the same set of parameters, more or less, is used for the electron donor. But if you, for example, do an experiment where a little bit of electron acceptor is added, only 20, you could assume we have H2 saturation, so we have lots of electron donor available, and you see there is no Km, so that means the maximum speed is running all the time, and we have high values for Vmax. Here 10 and 10 means within a second 10 nanomoles of the electron donor can be oxidized, and if we only added 20, then this will not be the limiting factor. So you can learn a lot about the limiting factors of processes. You can also do the other the experiment the other way around, that you have lots of electron acceptor and then add a little bit of donor. Both is possible. And last not least, you can add some calibration pulses of protons or KOH or NOH to titrate the system, the suspension back to the original value, and to use these for calibration of your buffering system. Okay, that's what you put in. Sounds more difficult than it is. Look at the following tutorials to see how it can be applied. And what does the program deliver to you? The output is a data table that can be saved in a CSV format, so it can be read by any text editor or spreadsheet program like Excel or so. And it will show the pH, it will show the electron acceptor that is still there, it will be the reduced form. In case of sulfate, it would be H2S or sulfide. Then you can learn how much ADP was conserved, what is going on with the membrane potential. And you see this is starting with your start value that you have put in, and then you see it will change, and after some time it's back to the original value. You can look at the intercellular pH. You can calculate the PMF, the proton-motive force, from both of these parameters. And you also get some interesting data about your cells from the bio numbers. So how many cells do you have in your assay? What is the intercellular volume of this? And you see it's very small, 1.3 microliters. What is the membrane area of your cells? This is huge. So that will be 122 in our experiment here, so much bigger. Membrane potential and membrane area are quite important. Plus minus per cell means how many charges are forming the membrane potential, and 150 millivolts. And you see each cell has minus 34,000 charges, which form the membrane potential of 100 millivolt and 150 millivolt. And the intercellular pH, and the cells have very low concentration of protons because the pH is very close to 8. That means there are only 5 protons. Look the previous introduction to explain these numbers. And so these are some bio numbers that are also delivered. And, the second thing it delivers is a graphic, which is scalable, and then you can make an overlay of the simulated curves here, various curves that you can generate of all of these parameters, and the real measured data curves, and then you can make the fitting very easily. Look at the upcoming tutorials to learn how it is done in real time. Okay, that's it already. Thanks for watching, and give it a try.